Welcome back. Last session we considered about the field lines and flux. So, flux is very important quantity when we are dealing with something called electric field intensity. So, in this particular topic we are going to discuss about the flux over a closed surface. The last session we discussed about flux through some elementary surface, some piecewise surface, but in this session we are going to consider flux through a closed surface. Now imagine that you have a positive charge, here and the field is diverging, or electric field lines are diverging out from there, and we are considering a surface, specifically a spherical surface around it, and again it is not a circle, it is actually a sphere like this. Okay, we are imagining something like this, not just a 2D thing, we are imagining a 3D thing. That is, we have a positive charge at the center of amount, charge of amount q at the center, and we have a circle of some radius, circle, not the circle, the sphere of radius, let it be r. So, we are considering a sphere of radius r. Now, we want to calculate the total flux over this surface. Okay. Now, we know that the equation for a flux is, phi is equal to, that d phi is equal to E dot ds, where E is the electric field, d is the area vector. So, here we need both. Imagine that here r is the radius of that sphere. So, over this sphere, over every point at this sphere, the magnitude of the electric field will be the same, not the direction, only the magnitude will be the same. Why? Because all the points on this blue circle or the sphere is equidistant from the center, from the charge. So, that value will be E is equal to 1 by 4 pi epsilon 0, that q divided by r square, and its direction is along r cap, let it be there. That means I am considering a particular point here. So, here this black line, this field line represents the direction, that means it is directed here like this. Okay. Now, it has the direction something like that. Now, we want to find E dot ds. For that we are considering a small area, okay, a small area here, a patch of area, okay, let me call it as ds. That area has an area of ds, its area is ds. Okay. Now, what is the direction of this particular area? So, already we have told that area always has a direction normal to its surface. So, that means suppose I have an area something like this, okay, then this will be the direction. Now, this is, you can consider this small patch as a flat area and it has a normal, and let me draw that normal in another color, something like this. So, let this be the direction of that area, and we may have a doubt, that means it is a surface, it is a sphere. So, it can have an area inward also, that means a single plane, okay, it is a single plane, actually it can have a direction towards here and towards here also. But there is a convention, that is, if you are considering a closed surface like this, then we have to take the direction of area always outwards. You cannot have a direction inward, you have to always take the direction outwards, because it is a closed surface and it is a convention followed. Now, let us calculate. Now, this is the electric field at this point is E, okay, and its direction is also along r cap. So, consider only this point. Okay, I am just magnifying that portion only. We have a curve and a small patch of area there, and in that area there is, in that area we have an area normal as well as an electric field E. So, both has, that is E and the area ds, both has the same direction, they are parallel. The first vector, this larger vector is the electric field and the smaller vector is the area vector, and they are parallel. That means, if two vectors are parallel, then the angle between them theta is equal to 0. Okay. Now, what we want to calculate? We want to calculate E dot ds, or this d phi. So to calculate E dot ds, we have E, okay, this is the direction of E, ds is the direction of the area and its value. So E dot ds means we can convert it into E ds cos theta. So this is equal to E into ds into cos theta. What is theta? Theta is the angle between, when we are taking dot product between two vectors, that means some a and a b. So a dot b means AB cos theta, that is where theta is the angle between them. Here theta is the angle between the E vector, that is this one, and there is another vector ds, that is the smaller vector. So the angle between them has to be put here as value of theta, and here we know that both vectors are parallel, so the direction so the angle between them is 0, that is why we can put it as 0, and we know that cos 0 is 1. So the answer will be E into ds. Okay, these two are different actually, E dot ds and E ds. This is completely a scalar value and this is a dot product. Actually we calculated the dot product to get this result E ds. So now we got a flux through this small area, only through this small area, not through the whole surface. What we have to calculate? Total flux over a closed surface. Our closed surface is a sphere, so we have to calculate the flux over this total surface. We have only calculated over an elemental area of area ds. So let us calculate that. We already know that how to do that. We have to consider many such areas. That is something you have to consider, another area here, another area here, and just sum it up, and we will calculate each d phi's and d phi plus d phi plus etc. So instead of doing that, so the total flux is equal to d phi from here, d phi from here, d phi from here. Instead of that we can integrate it. Okay, that is equal to integral E or integral d phi. So integral d phi, or which is equal to integral E dot ds, okay, and we are actually calculating it over the entire surface. So or it is a closed surface. To show it is a closed surface, we put a circle here. So whenever an integral is closed, we use this symbol, and it says that it is a closed surface. Now we are taking from this symbol, we are integrating over a closed, and ds means an elemental area. So we are integrating over a closed area or closed surface. So we have to do this E dot ds, and already we know that E dot ds is E ds. So this is equal to integral E ds over the closed surface, and we can take this E outside. Why? We cannot do it always. Okay, here we can take E outside because the value of E, the magnitude of E at every point on this surface, we are actually considering this area, this area, this area, each elemental area, but over this entire surface the value of E is a constant. So since it is a constant over the entire surface, we can take it outside. If it is some other random surfaces or something like that, we cannot easily take it outside. So that is something we have to consider when calculating the total flux, and we will deal about it later. The importance of this spherical shape will be dealt later. So we can take E outside. So taken E outside, E ds. Now what is this integral ds? So closed integral ds means you are taking a small area here plus another area here, another area here, and you are actually summing up the total area, total surface. We are finding the total surface area of a sphere. That means when we take all such kind of elements, you get the total area of a sphere, and the radius of this sphere is considered as r. Then the total area will be, so the total area of a sphere will be 4 pi r square. So I can write it as E into 4 pi r square. So now instead of, now we got E into 4 pi r square, where 4 pi r square is the total surface area of the sphere. Now we can substitute here instead of E. So E stands for the magnitude of the electric field at that surface, not the direction. Direction varies in each surface, but magnitude. If we take the magnitude of this alone, we can avoid this r cap and we can put 1 by 4 pi epsilon 0 q by r square here. Okay. Now we got phi is equal to some E into 4 pi r square. So instead of this E, we can substitute the magnitude of electric field at that surface, and which is already I mentioned, it's the constant over that surface. So its value is 1 by 4 pi epsilon 0 q by r square. Let's substitute that. So we got phi is equal to E into 4 pi r square, and the value of E, as we know, that is 1 by 4 pi epsilon 0 q by r square into, this is the E, and instead of, and the for remaining 4 pi r square. Now here we can see that 4 pi and r square got cancelled, and finally we got a result, that is q by epsilon 0. So the phi, the total flux, or we can put a suffix total here, the total flux over that closed surface is exactly q by epsilon 0. And what is this q? That q is the charge enclosed in that. That is whatever be the charge inside, that will come here. So we got a new law to find electric flux, or using this we can find electric fields also. So we got a law, and this law is called the Gauss's law, and Gauss's law states that, or says that, the flux over a closed surface, and we call that closed surface with a special name called Gaussian surface. Gaussian surface. So simply it means a closed surface, but we have to use some trick to choose a particular surface. That means we cannot, in principle we can use any surface, but for practical purpose we have to exploit what we call it as symmetry. That is, here what we chosen particularly a sphere. Why? We know that this electric field has a spherical symmetry. That means if we draw a sphere of radius r, and over its surface, everywhere over its surface, the field will be the same, the magnitude of the field will be the same. That is why we say that this charge distribution, or simply this point charge, has a spherical symmetry. That is why we chosen the surface as a sphere. So that is this Gaussian surface, and we got this Gaussian surface, and for that we got this relation phi is equal to 1 by epsilon 0 q inside, the charge inside. So there is, let me explain it more, and this is simply the Gauss's law. That is, you have a charge here, this charge can be either positive or negative, whatever it is, and Gauss's law says that, that is this phi, the total flux over the closed surface, is 1 by epsilon 0 the charge enclosed. Okay. So we spend some time here. That is, whenever you are considering, or we want to calculate the total flux phi, you have to only consider what is inside it. Maybe there can be some charges q1 here, q2 here, and some q here, and some q, let me call this charge as q, and some q3 here, and there is another q4 here. And for this particular case, if I write the Gauss's law, again consider that this is a surface, this is an arbitrary surface, it can have any shape. So here if we write the phi, that is the total flux, that total flux is equal to 1 by epsilon 0 times the charges. What are the charges here? That is q, that is something inside, plus there is q1. You don't need to consider the q1. Why? Because it is outside the surface. Here this is the surface and q1 is outside, so you not need to consider that. An outside charge cannot contribute to the total flux. It can have a flux, but the field lines entering and leaving will be the same due to this charge. So there is no need to calculate, or no need to consider this q1 here. So q, then q2 is also outside, no need to consider, but q3 is inside. So q3 plus Q4 is also outside, so this much only, or simply we can write it as 1 by epsilon 0 summation over Qi. So, and note that these charges are all enclosed, these are all enclosed charges. This is what Gauss's law states. So, if we want to calculate the flux over a closed surface, then that flux will be is equal to 1 by epsilon 0 times the total charge enclosed. Now, next thing, that is we can choose any surface, any type of surface here, that is here I have chosen a random surface. The Gauss's law is valid for every kind of surface, we can choose, but when we are applying that to a particular kind of charges, we have to think about symmetry. Practically we cannot do it with all even though Gauss's law is true for every surface, it is not useful for every surface. So, we need some kind of symmetry there to apply Gauss's law. We will deal with it later when we consider the application of Gauss's law. So, keep in mind that we cannot choose any surface area, any kind of surface, but it is theoretically it is true for any surface, but practically we have to exploit symmetry, and you have to only consider the charges inside. Okay, that's about Gauss's law. Now, we can write it in an integral form, like that is phi is actually the total flux. So, total flux we can write it as, we know the flux is E dot ds. Okay, that is a flux through an elemental area, and for a total flux we use something like this, that is it is the flux through a closed surface, that is what is calculated. This phi means it is the total flux. So, total flux can be represented in an integral form like this. This is equal to 1 by epsilon 0 times the charge enclosed. Now, imagine one more thing, that is instead of a point charge, so instead of a point charge, imagine we have a charge distribution. That means here you have a charge distribution, that is not a single charge, the charge is distributed inside. Okay. So, imagine something like this, the entire shape has some charge, okay, and let that charge has a charge density rho. So, the charge density of this distribution be rho, and then how can we calculate or how can we modify that Gauss's law? Let us see, if rho is the charge distribution, we know that dq, that is the elemental charge dq is equal to rho d tau. This is already we have covered in previous sessions, that is dq. Here we can consider a small amount of charge, that small portion, that is dq, that dq is equal to rho d tau. Now, to find the total charge, you can just integrate. So, integral dq is equal to integral d tau. So, this is the total charge. So, to find the total charge, if it is a point charge, just calculate q1 plus q2 plus q3. If it is a charge distribution, you have to integrate over the total volume. So, it will modify it into rho d tau. So, this is another form, or this is particularly useful for a charge distribution, and this is useful when we are dealing with some discrete charges, and for both the charges should be the rho d tau is the total charge which is also enclosed by the surface, that the charge should be inside. Okay, that is about the Gauss's law. So, that is here we have written, that is integral E dot ds is equal to 1 by epsilon 0 rho d tau. So, we can find the, so this is the Gauss's law, and we call it as the integral form of Gauss's law. This is called the integral form of, so we call it as integral form. So, there is another form called differential form also. We will see that in the next session. Now, we reached in the integral form of Gauss's law, and we can use this particular law to find the electric field due to many objects very simply, and that is the advantage of this law, but again mentioning that we have to use the symmetry. So, from the graphical representation of electric field lines and using the concept of flux, we reached at something called Gauss's law, and before we are going to apply it, we have to find another form of this, that is called a differential form of Gauss's law. So, next we will go from this integral form to the differential form. Later we do some applications of Gauss's law in the coming sessions, and thank you.